Things that I want to talk with you about. The first one is electronegativity. Electronegativity. Electronegativity is a number. We can be represented as a number that is actually a calculated number. It is a combination, sort of a weighted combination, if you want to look at it that way, of different quantitative properties of elements. And those quantitative properties can have been placed together or combined together mathematically to come up with a scale of electronegativity. On the periodic chart that I gave you, that I handed out, on this side, if you look at the key, this is the key down here, and you'll see that electronegativity is in the top of the column to your right hand, the far side. And so you're going to see some numbers like for sodium 0.93, for fluorine 3.98, for aluminum 1.81, things like that. In other words, it's never greater than 4. Actually, never greater than 3.8. Now, at the top of the periodic chart, right up here, we have some numbers, and it says rows of numbers, and it says percent ion character of a single chemical bond. We only assess the electronegativity of bonds. That's all we really care about, because we're trying to decide whether or not a bond is going to ionize or not. Well, why do we want to do that? Then we can decide what solvent to use to dissolve it in. Because if it's a polar solvent and we have a nonpolar salt, it won't dissolve, usually. Sometimes it will. Sugar is nonpolar. It shouldn't dissolve in water, except for one property that water has that makes it almost a universal solvent. Not quite, but almost. On the other hand, I don't want to put an ionic substance in gasoline. Gasoline is not ionic. It's not even polar. And I take, if I put an ionic compound in there, it'll simply sink to the bottom of the liquid. It will not dissolve. Okay, so part of the utility of determining the electronegativity of a bond in a molecule is to help you decide what solvents to use in order to conduct your experimentation. This is a decision that actually is not left up to you. As students, we try to make it for you, but we want to show you how we made the decision to use the solvents we did. All right, so that's what you're going to see on this chart. I think the last time we met, we made the determination that for some ionic substances, for example, let's take potassium. We found that potassium can readily become an ion by losing an electron. This represents the fact that there's an electron here represents the loss of an electron from here, because this is the only source of everything on the right-hand side of the arrow. Well, we were drawing this like a dot. We were saying, well, that's because this is in group 1A. And we know that being in group 1A says that it only has one valence electron. It only has one valence electron. And there it is. There's the dot. And here it is again. No dot. But there's the electron right there. We also found out, or we have found out, that for substances like, say, bromine, it has a whole bunch of valence electrons. It has 7 of them. Why is that? Because it's in group 7A. 7A, 7 electrons. Probably get it. And then this will readily take on an electron. And in doing so, it produces bromine with a negative charge. It has 1 more electron than it does protons. Therefore, it has a net negative charge, and it has a stable octet of electrons, meaning 8 electrons. Okay? So we know these two ions can form readily in the right kind of a chemical environment. What kind of environment is that? With each other. With each other. Why? Because potassium is going to give its electron to bromine so that potassium can now have a plus charge, net charge, and bromine will have a negative net charge. That's why. And what kind of a solvent are we going to do that in? Well, we're going to have to find that out when we discover, when we put all of this together, this part right here, I'll just do it this way. That's a compound, and we find we have, I'll just draw the electrons here. We have a net negative charge and a net positive charge on that atom in that molecule. Okay? Now we would like to know, we would really like to know, is this really ionic? I mean, we're drawing electrons and we're drawing plus and minus signs, but how ionic is it really? How ionic is it really? Well, you probably noticed in the assignment, part of the assignment in the laboratory, that you were charged with the job of calculating a quantity called delta E. The capital Greek letter delta, in this case, stands for change in, just the change in. And in your book, you probably could have found out, or did find out, that the difference in the absolute value of this number that I pointed out to begin with here, I read a few of them off, called the electronegativity of the atoms. We take the difference, the absolute value of the difference, we come up with a measure of the electronegativity of the bond, and that's what we want. So let's take a look at our chart here, and we see that potassium is 0.82. Value, and bromine is 2.96. Is that right? Mm-hmm. Yes. 2.96. So we take the difference in these two, or add them algebraically, and we're going to get 2, 1, 4, and it'll be positive because we're taking the absolute value. And this is our number. This is the electronegativity for the bond between potassium and bromine. And so we'll just call it equals delta E. Okay? Now, so what? So what? You still have this in your grubby little hand. And so you take a look right at the top, at that chart I was telling you about, and you find 2.14 on the top part of the chart, the one that has numbers, decimal numbers in it. And you come over here and they give you 2.1 and 2.2, and the midpoint is roughly, is close to this number right here, 2.14. So we go right down below that, and we notice that's the percent ionic character. And so we find that it's between 67 and 70%. Let's call it 68.5%. So this implies 68.5% ionic character. And what percent is it covalent? Anyone? Just tell me what the math is. What's left over here? So this particular compound is really quite ionic, but it's not perfectly so. It's not completely ionic. It has some ionic character. Okay. This is what that's for. Now, this was for an ionic substance. Let's look at a covalent substance, but let's take a pure, what we call a pure covalent substance, a substance that has absolutely no ionic character to it whatsoever. Well, if you look at your chart, let's back into it. If you look at your chart, you see that the percent, it's a 0.5% ionic if the change, if this number here is 0.1, if it's 0.1. Well, let's see, maybe that's a way we could figure it out. How would we make the difference in electronegativities of the atoms very, very, very small? Well, what if we had a molecule that had two atoms in it that were the same? They'd have the same electronegativity, and so if you subtracted one from the other, the delta E would be 0. Doesn't get any lower. All right, well, not as an absolute value anyway. So we look at that and say, well, that's going to be less than 0.5% ionic. That means covalent, from the point of view of being covalent, it's 99 plus. Covalent, pure covalent. Now do we know any molecules that will bond with themselves? That's right. Who said that? You're absolutely right. Pat yourself on the back. But that's true. Hydrogen has one electron, and if we take two of them, normally I would just put a 2 there, but I'm kind of lightening up on you. And that would be the reaction right there. And what is this? This is sharing. This is covalent. This is a sharing bond. So I want to impress upon you that we're always talking, when we make this delta E measurement, we're trying to characterize a bond between two atoms. We're not concerned with the atom itself. In other words, we will never measure these numbers up here. These numbers right here, like in the case of the bromine, the 2.96. We don't measure that number. That's calculated. That's a calculated number. What we will do is estimate the percent of electronegativity or ionic character, or covalent character, that a particular molecule has. Now, if you look at the periodic chart, can you guess? Let's see. Let me take it. Can you guess? Looking at this side, the one that says table of periodic properties of elements. Fluorine has the highest electronegativity, and the lowest one is francium. And you can satisfy yourself that that's true by reading this probably just before you go to sleep at night, because it'll put you to sleep just like that. Just like that. So the thing is we want to, let's erase this, just so we can have a bit of room. And let's look at the electronegativity of francium and fluorine. Francium fluoride, the most expensive chemical on Earth. It's going to be, well, the E for the francium, Fr, is equal to 0.7, and the E for the fluorine is going to be equal to 3.8. And so we're going to take the difference in these two, and we're going to get 3.28. That's the maximum difference. That's the maximum difference we can find. And now if we go up here to this top chart right here, this top row of numbers here, and we look for 3.28, we find it. It's greater than 92%. So this compound here has a delta E that is greater than 92, and we'll express it as percent. That's actually, it's greater than 3.28, and that implies a electronegativity, a percent ionic character greater than 92% ionic. There's none higher. There's none higher. That's the most ionic substance on this chart. You can actually calculate it. One of the things about ionic substances, we often make the mistake that an ionic substance is more soluble in water than others, and that's not necessarily true. There are other factors that affect solubility. One of the main factors in the determination of the electronegativity, however, is the what's referred to as the ionic radius. Now, if you look at this, well, let me draw a picture. First of all, yeah. Not quite, but close. There's a nucleus of two atoms. Let's call this fluorine, and let's call this one O for change sodium. Now, the ionic radius is, or excuse me, the atomic radius is this number right here. It's that distance. It's that physical distance, and we measure that. We measure that in the laboratory, not unlike the laboratory that you work in. It's not a theoretical consideration. I mean, it works into them, but it is not a them. And so we'll just call that A for, and then this distance here, A for fluorine. And we find, and this is for Na. And we find that the distance separating these substances is going to be less than or equal to the sum of those two radii. And so we can calculate it that way. What we find is, however, that as the radii get very, very small, the electronegativity has a tendency to get small, but not terribly small, because it's already small. That is to say, each radii. But when you have a large radius and a small radius, like a nonmetal and a metal, in the case of fluorine and sodium, when you have those two, now you have a chance for a large ionic radius. And the electronegativity, however, isn't as large as it could be. We calculated it for francium fluoride, and that was a very, very big molecule. It had a lot of electrons in it. Therefore, what I would point out to you is that the size of the atom plays a very complicated role in determining the ionic or covalent character of the bond. But what I want you to realize is that it's all over the map, all over the map. Things can be very, very ionic. They can be almost not ionic at all, pure covalent, in fact, or anything in between, anything in between. Before you came to class today, probably, unless you've studied this on your own, which I probably feel pretty safe in saying, maybe not, but maybe, you didn't know that. You thought there were two kinds of bonds, covalent, sharing bond, and ionic, bond that involves a transfer of electrons. Well, it isn't true. It was a kind of a fiction that we permitted you to indulge yourselves with. But now the truth is out. We've come clean. The bonding between atoms can be covalent with some ionic character, or ionic with some covalent character. And we actually have a name for the elements, or excuse me, the bonds where the delta E is less than 0.4. These are said to be nonpolar, covalent. Notice that it would also include a delta E of 0, right? The way we had with hydrogen. For delta E, greater than 0.4 and less than, and now we need to find the 50% point on the scale. We'll say 1.65. This is polar covalent. I'll come back to what this means in just seconds. And then for delta E, greater than 1.65, these are ionic. And all ionic bonds are polar. All ionic bonds are polar. So we would call this polar. Now, what do I mean by that? I mean that in the case of water, for example, hydrogen is bonded to oxygen, 2 of them actually, and it has some extra electrons. We have a total of 8 electrons. And if we do the electronegativity calculation for one of these OH bonds, we'll have, let's see, 2.1 minus 3.5, is that right? 4.4. 3.44, and so delta E, that's what it equals, and that's going to be 1.34. 1.34. That says that bond right there has a ionic character of, it's only about 36%. 36% ionic. This implies 36% ionic and 64% covalent. And this is why we write this. We say this. That's a lowercase Greek delta. And in this notation, all it means is it's not a full charge. It's not a full charge, it's a partial charge. So we only have a partial positive here. We don't have a full-on partial, a full-on positive charge the way we would in an ionic substance, like sodium chloride, for example. In that molecule, it has these charges. That's a full charge. That's a full charge. Because it's very, very ionic. But this isn't very, meaning this oxygen only attracts that hydrogen's electron just away, just a little bit, enough so that this is more negative than either one of those hydrogens there in the molecule. So that's across the bonds. The bonds are poles, dipole. We call them dipoles. One's a positive charge, one's a negative charge. Or you could say one's a north pole, one's a south pole. It doesn't matter. It amounts to the same thing. Only it's not as strong. This is not as strong as this north pole. This north pole is weaker, but it's still north. These two would repel each other like magnets, okay? So we can actually indicate and we will, and your book does, if we indicate the extent to which a bond is ionic by putting this partial positive charge here, partial negative there, partial negative there. Why this is partially negative is because all of these electrons have been scooted over to be closer to the oxygen than to where they belong. So now it has a partial there and partial positive charges, or north pole, if you want to call it that, partial south pole. Okay, so this is what we really want to emphasize is the almost continuous charges or magnitudes that this thing right here, this thing right here, and this thing right here. Okay? Okay, now you can turn it off if you want.